on the homework, what you're doing is you're trying to find a series that you're going to compare these to, and then you do your limit. And as long as the limit works out to be non-zero, you're going to say, oh, they both share the same fate. So what sorts of problems did you have? Is there anything here, or maybe you're ready to go on ahead? What do you think, Michael?
Was it possible to use the other method for these?
It was. It was.
That method at all, and I was kind of
Wait, you didn't use the limit method at all? Okay. Okay. We should be clear, though. It is possible for some of them, probably all of them. Some of them may have been a little bit harder to fit into that method than others. So just to be clear, that like, for example, I don't know, I'm just looking at this, for example, number 15. 15 is easy with the limit. I don't know if that's one that you had to do, but this one would be pretty easy with the limit comparison test, a little bit harder to get it to fit into the direct comparison test, just saying. So some of them are a little bit harder. Generally, you can use either test, but the limit is usually easier. So we should at least do one limit, because all of the ones that I have on the quiz are a lot easier with the limit than they are with the direct. So I don't know if any of them were like, if it was a struggle to get it to fit, maybe not. Okay, you don't remember? Okay, that's fine. But did anyone else have trouble getting, like, picking and then doing the limit? Maybe we should definitely do at least one or two of these just to make sure, because we're going to do a limit. What do you think, Daniel? Oh, there are factorials? Which ones? Let's see, where are they? Oh, yes. Wait a minute. Am I looking at the same thing you're looking at? Do I have the right page here? I don't? Hold on a sec. This isn't section 11.3? Whoops. Hold on a sec. I'll get it here. Just a sec. Sorry about that. I don't know what I was thinking. Oh, yeah, that was the integral test stuff. No wonder. Okay, just a minute. I'll get it up there in just a sec. It'll take me a sec to do the conversion. Sorry about that. If you were looking at that thinking, oh, that's not right, yes, you're correct. Yeah, I'm a little scattered today. Okay. Spoke with a colleague. She said she was late today, like later than normal. And she's like, yeah, everything's dragging today. It's like, yeah, I feel you. Okay, here it is, 11.4. 11, this looks better? Okay, give me a sec. Let me just pop this into Notability so I can write on it, then we'll be good. Okay, so you say 29 and 30 had factorials? Yes, they did. Oh, I love it. Okay, so what are we going to compare this to? Interesting. Yeah, that one I'm going to use a direct comparison, actually. I wouldn't want to use a limit comparison. So let me look at my homework. Why did I not assign anything that were obviously, hold on a sec. Homework zone. This is the stuff that's due today. Be sure to show all work. Okay. Let's see, 29 and 30. Yeah, I would use a direct comparison with these. We can do those if we need to. Let me just circle the ones and I'll pick one. I'll pick at least a couple of them to do. And we can do the factorials, yeah. 23, okay, that one I would definitely use a limit. I'm sure you could do it with a direct comparison, 22. There were a few others. Let's just do one of these. We can do more than one, but let's do this one here, just to show you how this works, just to make sure we're all on the same page. So looking at this, what I'm going to compare this to is I'm going to compare it to this. I'll explain why in just a sec. And the reason why is because I'm taking the highest power term in the numerator, n, and dividing it by the highest power term in the denominator, which is n squared into the fourth. So when I do that, I get n over n to the fourth, which is 1 over n cubed. That is a p series. So if you want to know what do you have to write down, here's what you have to write down. P, okay, actually, I probably would be like this. This is the minimum. I know some of you don't want to have to write anything, so I'll show you the minimum. That's a p series, it converges. I know you probably should write this down as well, but I'll put this in a different color. P is equal to 3. But if you write that down, the stuff in red, I'll probably overlook that you didn't write the p equals 3 and be happy. Next, you're going to make a limit. So in this case, since this is so complicated, it's going to be difficult to get an actual direct comparison to that, but it's easy to do a limit. Here's what the limit looks like. Limit is n approaches infinity of, let's see, any one of these can go on top. I don't care which one. 5 plus 2n over 1 plus n squared squared. So we're going to have to do a little bit of algebra, but it's not too bad. This is going to be 1 plus n squared squared over, whoops, I need my limit. N approaches infinity. And this is going to be 5n cubed plus 2n to the fourth. Sorry, I just multiplied. I did two things there. I flipped and multiplied. And when I multiplied by n cubed, hopefully that doesn't shock you. I guess I should do one more thing. There's the numerator. I always forget the limit. I remember when I was, this is like 45 years ago, 40 years ago, sorry, making myself out to be older than I am. But I remember taking Calculus 2 and all the limits, I wouldn't write that. So if you don't write it, I'll just be like, yeah, I remember, it's a pain, but you should write it. Anyway. So there it is. And then this limit is pretty easy since you have two polynomials, just 1/2. 1/2 is finite, 1/2 is non-zero. And so that means that these two series are linked. Since this one converges, the other one converges. All done. So that's what the limit comparison test is. I have chosen for the quiz problems that would be hard to do, harder to do, I should say, using the direct comparison. Let's take a look at these factorials just briefly to see how I might do this. So this n factorial over n to the n. Okay, first of all, 1 over n factorial. How are we going to do this? So this, the way I would do this is I would say that 1 over n factorial is going to be smaller than 1 over n squared, as long as n is greater than or equal to 3. Now you might say, how do you know that? Oh, as long as n is greater than or equal to 4. So you might say, how do you know that? Well, think about factorials. Factorials, you're multiplying n times n minus 1 times n minus 2 times n minus 3, etc., etc. So you keep multiplying a bunch of stuff together, whereas this is just n squared. There's only 2 factors in that product. So as long as you have enough factors together, you're definitely going to be bigger than n times n. And you can do a little bit of testing to see that this is the case. For n equals 4, 4 factorial is 24, and 4 squared, of course, is 16. And this is definitely going to be the case beyond this, because when I go to 5 factorial, I'm multiplying 5 times this number. This is a number bigger than 5, whereas 5 squared is 5 times 5. So 5 factorial is 5 times 24. 5 squared is 5 times 5. The same thing will be true of 6 factorial. 6 factorial will be 6 times this big number, 120. So 6 times 120 is 720. 6 squared is just 36. So for sure, this will be the case. And that's our direct comparison. This thing converges, so this one converges. You can do something similar with this one to show that those converge. Excuse me. So that one converges. That one's a little bit trickier. Here's how I might do this. N factorial over n to the n. What's that going to be less than? Here, let's do it this way. So you have n over n times n minus 1 over n times n minus 2 over n. Okay, I think that's enough. Let me get rid of all of this. Yeah, now I'm doubting myself. Does this thing converge or not? Oh, I know. Yeah, this will work. Times a bunch of stuff times 2 over n times 1 over n. Okay, there we go. So that's what n factorial is. And so that thing is going to be less than or equal to, so n factorial over n to the n will be less than or equal to n to the n minus 2 over n to the n times 2. So where am I getting this n to the n minus 2? It's, I'm just increasing each of these numerators. So n is bigger than n minus 1, n is bigger than n minus 2, and so on. I'm going to increase each of them except for the last two. So this equals 2 over n squared, and you're back to the same boat. That thing converges, so this one converges. So yeah, it's a little tricky. Yeah, I don't know how, I honestly, yeah, that one I think you have to use direct comparison. So if you did the direct comparison and got that converged, well done. That one is a hard one of the bunch. So what about these others? Anything that doesn't have a factorial that we need to look at before we do the quiz? The quiz, there are no factorials. Yeah, Hayden? I haven't got your test written yet. I can say that you will see factorials eventually on tests. So eventually, because they're so important. They're so important for what, like this all seems like a game, and you're like, what does this have to do with anything? Well, when we get back to reality, it will no longer be a game. It'll be like this function has this series representation, and it'll have factorials in it. So eventually, so at the very, for now, we'll have plenty of factorials in our lessons as well. For now, just be aware that n factorial is n times n minus 1 times n minus 2. You keep multiplying till you get to 2 times 1, and so on. This is a huge number. So like 5 factorial is 120, 6 factorial is 720, 7 factorial is 5040. They just keep getting bigger and bigger very quickly. So this thing grows really quickly. So, but yeah, they'll be important eventually. But for now, I'm trying to think, will they be on your test next week? I don't think so. You know, because we haven't had them up until now. This is the first time. But they will appear soon, and they will be important soon. So the final for sure. Anything else? Other concerns, or maybe there's one back here that you're still not sure of how to do the limit comparison test for. Yeah, what do you think, Maggie? Yeah, let's do 16. That's a good one to start or to finish things up. 16. Darn, that's another direct comparison. Yeah, so yeah, I would use a direct comparison with 16. I should have, you know what I did was I took all of the homework that I think I told you this on Wednesday. So I took all the homework, or maybe I told you Tuesday, all the homework that I used, you know, a few years ago, and I just said, oh, I've already got this all written up. I'll just put it in there. And so I didn't preview this before. So yeah, 16, here's how I would do 16. 1 over n to the n is less than 1 over n squared. Once again, I keep harping on the 1 over n squared thing, but it's a good one because 1 over n squared we know converges. So this for sure, if you think about it, 1 over 3 to the third is less than 1 over 3 squared. 1 over 4 to the third is less than 1 over 4 squared, and so on. This is going to be true, I guess, for every value of n if you do that, because n equals 1 and n equals 2, they're equal. But every other number, you're less. And so you have this series is less than a convergent series. And so that's a direct comparison that converges. Yeah, maybe I should pick one that we actually, like number 22, we'll actually do a limit. So let's do number 22, just so that we have one more limit comparison. Yeah, anytime you have something more complicated. So here's how I would do this if I were you. If you have something simple, like that or this, then direct comparison is fine. It's just, you know, whatever. But if it's at all complicated, like these down here, I'd say limit comparison is the way to go. So let's take a look at 22 briefly, and then we'll see if you have any final thoughts before we take a look at the quiz. Cut this out. So here, so this one, we're going to do compare this to this. So I've got n cubed on the bottom, n on the top, our friend 1 over n squared. So that's what I want to compare this to, because I use the biggest term on the top, biggest term on the bottom is n cubed. So let's do a limit. This one we know converges because it's a p series. So we're going to do the limit as n approaches infinity of 1 over n squared over n plus 2 over n plus 1 cubed. So let me just do this relatively quickly. So a little bit more algebra. And you might even skip this step because it's so obvious, but I'm going to write it down. So what I mean by this is when you get to there, you might say to yourself, hey, this is n cubed times a bunch or plus a bunch of other stuff. And so this is going to be n cubed on the top, n cubed on the bottom. The limit is 1. That would be, I would be happy with that. But technically I should do this. And then you're like, hey, there's the leading terms. And so that equals 1 as well. So we have linked the two series. And since the first one converged, the other one converges as well. So they both converge. So that's what I'd like you to do. In fact, to shorten this up, let's only do 2 of these because I've got 3, but let's just do the first 2. If you get excited, you can do the third one. I know you want bonus points, don't you? Yeah, you can have bonus points if you do the third one, but I'm not going to sit and wait for you to do the third one, all right? Do the first 2 and then be happy. Here, send these back if you have too many. So let's see. Sorry, trying to peel them off here. Here. Oh, did I just throw them on the floor? I don't know if there's enough there. There's definitely not enough there. You need one? Nope. Here you go. You can have a few. There may be enough for the people behind you, in fact. Here, we'll give one here. Here, I'll get more for you. Don't worry. This is extra. This is extra. You've got 1, 2. Good. You need one? There, right there. He's got several. You want me to have that? Thank you. You have 3? Okay, good job. Okay, these are for the absent people then. All right, well done. So do numbers 1 and 2. You can do 3 if you have time, but don't dwell on it. And I'll get this for the people watching from home. Okay, there it is. Okay. There's that. There's that. All right, hopefully you're closing in on those first two. I've got all three of them done, but I'm a professional, so if you want to, if you're all done with the two and you're happy to not do the, well, or you did the third. Okay. Some of you are frantically doing the third one. That's fine because there's still people doing the first two, so that's fine. Oh, you're all done? Wow, you guys are quick. Incredible. All right. Oh, someone dropped something. Who is this? It's all right. I'm wandering around. Yeah, you're happy with those? Good. Good job. You're happy? As happy as you're gonna be. Fred, are you okay? Because these guys, they said they were gonna kick you out of your normal seat. You're struggling over here? Well, if you don't do as well on the quiz, I'll know why. So sometimes you have to be in the right seat.
All right. Okay.
Yeah, figure it out. That's right. What do you think? Wow, you're incredible. Good job. Whoa. Everyone took this as a challenge apparently and is cranking out all of them. Nice job. Yeah, they are. I'll let you know. I'll start. Once I see that everyone's on the third one, I'll start just ripping them out of your hands. Good job. Nice. Excellent. You should do this every time. You guys are quick. Quicker when you have a challenge. Nice job. Good job. Excellent. Still working. Still working. Let's see. Nice job. Still working. Yeah, we're still some people are still going on the first two, so don't worry. Nice work. Okay, all set. Good job. Good job. He's on third. Oh, you're on the third one? No.
Thinking about it.
You're thinking about it.
Yeah.
All right, because there's a couple other people still working on the second one. Peek here. Make everyone nervous. Oh, Connor never showed up. Huh. Now, if you use a limit comparison test here, since they have the same stuff as you do, you know, you
Yeah.
the conclusion is that you should win.
In theory, yeah.
So, or maybe it's a direct comparison test. Is that it?
I think this is just a losing battle.
Oh, come on, don't do that. Oh, I was so excited. What did you erase? Let's see. Yeah, that's good. Yeah, that's great. Now put a little box around something. All right, good. I don't know. What did you erase there? Wait, do you have something here? Here. Yeah, you did something wrong here. That should be on top. That should be on top. Here, just put that on top, the n squared. Yeah, it's algebra. I know algebra's hard. There you go. You can get rid of it down there. And then just say equals 1. Because it's going to be just a 1. Yeah, there you go. Now put a box around something. Oh, yeah, you expelled it out. Very nice. Yeah, that's perfect. 100%. Good job. All right, I'm coming around for all those who are still trying to get that third one. Oh, good job. Hey, well done. Nice work. Okay. Oh, no, you don't. Okay. All right, you got it. Good job. Okay, I think I got them all now. Do I have everything?
One more.
One more. Okay. Let's get it. Got to get it all with its friends. Oh, everything's yellow in here. Okay. Okay, they're all stapled together. Let's see what I did. Hopefully I got them right. I saw a lot of people that did something like this. So I was kind of quick with mine because I wanted to blow through this. So the first one I compared with 1 over radical n, which diverges because it's a p series. P is 1/2. Anyway, so I did this limit and I got 1/2. If you did 2 over radical n, fine. You'll just have 1 here instead of 1/2. I don't care. But the important thing is that this does show that these diverge. Then this one, because our friend 1 over n squared, because that converges, and I did that limit of these two, and I got 1. I was like, okay, those are both going to converge because 1 over n squared is a p-series that converges. I was kind of minimalistic here. Some of you wrote more than this, which good job. You should write more than this. I was lazy. Final one, for this one, I was comparing this with this series down here, 1 over pi to the n, because that's a geometric series, and geometric series converge if the common ratio is less than 1. So this one converges, so then I did this limit, and that limit turned into this, and then that was this after doing, separating into 2 fractions. So I have 1/3 minus this thing. That thing is a little bit of a problem, but I used L'Hopital's rule, at least I pretended to, and I got 0. So I know, I should have actually done it, but if you do L'Hopital's rule, you'll find that you do get 0. You only have to do L'Hopital once, by the way, not multiple times, but good enough. You knew that it was going to be 0. So there it is. So those both converge. Nice work. Okay, so today what we're doing is we're going to take a look at alternating series. Alternating series are series, at least we're going to get started on this. You might notice when you look at the homework that from here until the end, we are taking our time. This is because historically this stuff is hard. This stuff causes all kinds of grief. And so because of that, we kind of rushed a little bit before spring break so that we could slow it down. So alternating series we're going to do today and Monday, and you'll see that the homework matches up with that. Same thing goes with then we'll have a test. But anyway, so what is an alternating series? Well, so far we've been sort of fixated, I mean, not entirely, but for the most part, we've been dealing with series that have positive terms. I realized that some of the geometric series had alternating terms, but let's not worry about that for now. Most of our series have positive terms. Think about the integral test, positive terms. Think about the comparison test. You're required that they have positive terms to use those comparison tests. So, which is something I really should have done for each of those series on the quiz, but I didn't. Check that they were positive, but they were. There was no negative numbers there. So we want series with positive terms. Well, what happens if you have negative terms? Well, when you have negative terms, you have possibly what's called an alternating series. Alternating is exactly what it sounds like. We're alternating back and forth from one to the other, positive, negative, positive, negative. So think of alternating. So some series don't alternate, but also aren't always positive. So you need to have alternating to use what we're doing today. So let's take a look at what this means. This means stuff like this. Here are 2 alternating series. One of these series converges and one of them diverges. So, but you can see that the deal here is that we start off either positive or negative, it doesn't matter, but we go positive, negative, positive, negative, positive, negative, on and on. Alternating. Usually in an alternating series, you'll have something like this in the formula. Notice it's -1 to a power, but there are other ways to have an alternating series. For example, if I wrote something like this, if I had cosine of pi times n, that alternates. Because the cosine of pi is -1, the cosine of 2 pi is +1, cosine of 3 pi is -1, and so on. So you don't necessarily have to have a -1 in the series for it to alternate. There are other ways, and this isn't the only other way, by the way. So there's other ways to get something to alternate. So take a guess. Like I said, one of those 2 series that we're looking at here, one of them converges and one of them diverges. See if you can guess which is which, and then I'll show you how we're going to figure it out. It's really not all that, go back, come on. It's not that complicated. So this is one of the easier of the tests. So just to warn you, Monday we'll extend it and it'll become hard, but today's stuff is easy. So I hope you have your guess. Do you have it locked in? Which one is the convergent? Which one diverges? Well, here I've got a picture of the first one. The first one is, I should say that horribly faint blue, which you can hardly see, baby blue, sky blue, that is a graph of the terms. This is a graph of the terms. I'll show you the series in a minute. So the terms begin at 1, and then we're at negative 0.5, and then we go to positive 0.333, negative 0.25, positive 0.2. So you see what this line is. This is a graph of the terms, and so you can see alternating, bouncing up and down. Now let me show you what happens when you add these terms together. So when you add them together, you get this. Now it kind of makes sense. We start with 1, and then we're going to add a negative number to 1, and we go down here. But then we're adding in a positive number, and then a negative number. So of course the sum, because we're adding and then subtracting, like, you know, you get money, then you pay money, and so your wallet goes back and forth, but you usually have about, well, you don't have a wallet with money in it, do you? But your bank account or your credit card statement goes up and down as you as you go through life, I guess. So that's sort of the result. And notice what's happening to this series as we go forward. We're getting closer to this number, whatever this is. So we keep toggling up and down, but eventually it looks like this is settling down, doesn't it? That the limit will be some number. So this one actually converges. We'll explain why in just a minute, but this converges. Why does it not write? I don't know. Converge. So this one converges. Let me show you the other one. So here, I'll go back here and you can see it first of all. So if you guessed that this was the convergent one, well done. That is the convergent series. This one, does this converge or diverge? Well, let's find out. Here's a picture of the terms. So once again, these are just the terms. So this start at negative 1/2, positive 2/3, negative 3/4, positive 4/5, negative 5/6, and so on. You probably see what's happening here is that unlike the baby blue sequence of numbers, these numbers, they're getting further away from 0, aren't they? And so when this happens, check out what happens with the sum. When I add these together, we start off with negative 0.5. We add to that positive 2/3, you're up here. Then you subtract off 3/4, and then you add in 4/5. Well, you're toggling back and forth between, eventually, you never settle down. This black line, it looks like you keep going back and forth between two extremes. And in fact, that's what happens here, is that you never converge. You always end up toggling back and forth between two extremes with this one. And so this one actually diverges. So you can probably guess what the test is. Basically, as long as your sequence converges to 0, you're going to converge. If the sequence doesn't converge to 0, you're going to diverge. This feels familiar, but this is more definitive than the test. I'll show you my flow chart in just a minute. It's more definitive than that test for divergence, because this goes both ways. This tells you when something converges. So here's the rule. And there is this another little caveat that we have to check, is that thing, which we'll check it each time. But if you have an alternating series that looks like this, as long as the terms are getting smaller and the limit is 0, you have to have both of those things happen. As long as both of those things are true, then you're definitely going to converge. So this is more robust than the other. I'll show you on our flow chart that this is reminiscent of, but that's all we got to do. So this is actually a super simple test. You're checking 3 things. So here are the 3 things you're going to check. Does it alternate? So we'll check that off. Well, when we get to it, we'll be checking these 3 things. So does it alternate? Number 2, does it decrease? Decrease. And then number 3, is limit equals 0. So we're checking those three things. So let's go do this with some examples. Where are my examples? Is this an example? That is an example. So here's an example. Does this alternating harmonic series converge? Let me remind you of the three things you're going to check. Does it alternate? Alternate, which means, is it positive, negative, positive, negative? Well, anytime you have this in your series expression, you're alternating. So yes, this is a yes. Number two, are these decreasing? Now, by decreasing, I mean if you take the numbers and ignore the pluses and the minuses. So let's see, do we decrease? We have 1, then 1/2 is smaller than 1, 1/3 is smaller than 1/2, 1/4 is smaller than 1/3. I think you can see that no matter where you are in this sequence, wherever you are, you're going to be getting numbers that are smaller and smaller. Oops, there's no plus there. So no matter where you are, 1/10, 1/11. 1/11 is smaller than 1/10. Let's say we go out to 1/1,000,000. Well, 1/1,000,001 is a little bit smaller than 1/1,000,000. So this is decreasing. You can put a check mark next to that or say yes. Finally, the last thing that you have to check is, does the limit as n approaches infinity of the term, so we'll call it b sub n, does that equal 0? Well, let's check. I think you know the answer with this one. That limit, for sure, that's 0, isn't it? So that's 0, that's another yes, and because I've got 3 yeses, this one converges. That's all you have to check. 3 simple things. It's so much easier than the integral test, isn't it? So much easier. So this is a happy test, I feel. Something super easy. We could have done it in 10 minutes, but we're going to stretch it out to 15. Okay, so let's try another one of these. So you do this one. Does this one converge or does it diverge? I'll write down the 3 things you're going to check, and then I'll ask people to help me out. So we're going to check, does it alternate? Does it decrease? I'll help you with that one, because that one's hard with this one. And then limit equals 0. And I need to update my attendance because someone snuck in. Just a minute, who was that? Yes, you did. And you did. Wow, 2 people snuck in. So I only have one absent. Wow, well done. I know where he is though, so don't worry. He's watching the video now saying, I know where I am too. I exist. All right, let's see how we're doing. Let's pick some random people here. Random student. Darren. Darren, does this alternate? It does. Well, pretty much all of the things in this, you can pretty much assume, but you should check. Does it alternate? Here is that alternating. You see the -1 to the end. Well done. Next, let's see. Does this thing decrease? So Landon, what do you think of this? Well, Landon's not here. How did I miss that? Okay, so Ryan is here though. Ryan, does this thing decrease? It does. So this one's harder though. Let me just show you. I don't know how you did it, Ryan, but let me just show you how I would do it to check to see if this decreases. I usually do something like this. I have the nth term, and then I do the n+1 term, and I make a little comparison, and I say, which one of these is bigger? So let's see. How can we tell which one is bigger? Well, I suppose I could just multiply both sides, like do cross multiplying. So it's okay? You don't have to run off? You do have to run off. Volleyball again? Oh. You can watch the video if you want to catch the tail end of the episode. So I know you want to know how it turns out. Okay, so here, why don't we do this? This is what I'd like. I would like it to be like this. So if it's decreasing, so this is, by the way, decreasing, this is the hardest. This is the hardest thing to check. So if you're thinking this is going to be easy, you're right, except for that middle one. That's usually the hardest. And so you would be forgiven if you skipped it until the end, especially with this one. Some of you are like, I didn't even do that, which is fine in this case. It's sometimes not, but let's do it anyway. Does this decrease? I have a question mark there. Does it? Well, we can check by cross multiplying. Now, of course, when you multiply, when you're doing inequalities, you would, of course, be a little bit worried about whether or not you just multiplied by a negative number. Because if you multiply by a negative number, you have to change the direction of the little alligator so that it eats the bigger of the two numbers, right? So, but in this case, this is positive and this is positive. So we're okay. As long as n is big enough, those will be positive. And then let's see, do these this bigger? So let's do this, 12 in, wait a minute, I feel like I'm missing something. This should be an n here. Yeah, 12n squared. Let's see if I can collect everything together. Let's see, 4 times 1 minus 3, or minus 1 is going to be 3. So this will be plus 9n. I believe I did that on the right, left correctly. I did my algebra. And then on the right, I've got 12n squared. And then I've got 4n times, oh, wait a minute. I think both Ryan and I are wrong. Just a minute, 12n? Oh, no, this is also 9n, thank you. No, Ryan knew he was right. He's just thinking, yeah, this guy needs more coffee this morning. Yes, I do. Okay, here we go. So this will be 9n minus 3. Did I do that right now? Okay, let's pretend that my algebra is correct. So now I can say, yes, this is true. Yeah, notice that the stuff on the left is bigger than the stuff on the right because of the 9 minus 3. Okay, we got the last thing. The last thing's the easy one. At least I think of it. And so sometimes it's better to just do this one before you do this. Because if we did that one first, if we did the bottom one first, we wouldn't need to do the middle one. Here's why. Hayden's going to tell us why. Hayden, is the limit as n approaches infinity of this equal to 0? So let me write down that limit for you so that you can evaluate it properly. The limit as n approaches infinity of 3n over 4n minus 1, is that equal to 0? Okay, if you were to just be given this on your Calculus 1 exam, what is this limit? Leading coefficients into the first. What's this number? No, what's this number? What's this number? Very good, 3/4. I know you also need, you'll join me for coffee after this, and we'll get ourselves together. So the question is, does this, and the answer is no. The moment you get a no, if you have an alternating series where either of these is no, then, no, this is the important one. If this one is no, then it's going to diverge. So this one diverges. So you're checking these things. Let's do another one. This will hopefully help. There's 3 more here. So we need to know, I'll make a little table here, and then you can fill in the table. So you're going to ask yourself, does it alternate? Then you're going to ask yourself, does it decrease? And then you're going to ask yourself, is the limit equal to 0? Now, like I said, it might be helpful to just do the limit question first because it'll save you some work. Because if the limit is not 0, then you're definitely not going to converge. So let's do this for all three of these, and we'll get yeses and nos for each of these blocks in my table. So take a minute, see if you can do that. There. So in the lime green on the left, I've put the formulas, if you couldn't figure them out, for each of these series, because sometimes it's helpful to have that formula. If you can see it, given the poor color choice that I made. Maybe if I zoom in, it's still kind of hard to see, isn't it? Well, let's do this anyway. Braden, what do you get for this first one? Is this, we'll just do one at a time though. Don't jump the gun. Does this alternate? It does alternate. Very nice. Okay, so this one alternates. The next one, let us skip decreasing just for a minute, because as I mentioned, this is going to be sort of the important thing here is, does the limit equal 0? So, so Emily, does the limit of the terms for this one, does this limit equal 0? No. What does the limit equal? Okay, so we can't, well, no, it's not that we can't use this test. This is no. So this one diverges. So there you go. The decreasing thing we do have to check, but only if this is a yes. So it might be helpful to do it that way. All right, let's go to the next one. Fred, what do you think of this? Does this one alternate? Plus, minus, right? So this one does alternate. I should make that a yes. Okay, that looks really strange. Okay, well, anyway, check mark. Yes, however you want to say it. All right, next, Lewis. Does it go to 0? Is the limit of the terms 0? Yes. You can look at this here, and you can say, yes, 4 over n plus 7, if you can see it. It does go to 0. So the final thing is this decreasing? So let me just write it down for you, because this is hard. This one's the hardest of the bunch. So here's what you're checking. You're checking 4 over n plus 7. Is that bigger or smaller than 4 over n plus 1 plus 7, which is n plus 8? So which of those is bigger and which is smaller? And I think you probably know, you're not here, but you probably know, Hunter knows. Which of those, is it 4 over n plus 7 that's bigger, or 4 over n plus 8? That's right, that one's the bigger one because it's got a smaller denominator, so it's bigger, and so that's also a yes. Once we have all three yeses, we say that converges. Okay, last one, bottom one there. So let's go through our list. Does this thing converge or diverge? We'll start with alternating. Michael H. Michael, does this thing alternate? So if it alternates, it would have either like a cosine of something, or here a -1 to the n. Does this have any -1 to the n's in it? It does not. Okay, very good. So because this one does not, this one does not, so no. So what do we do with it? Well, we don't use the alternating series test, that's for sure. What we do is we go back to our little flow chart here. Let me go find my flow chart. Give me a sec. There, is this my flow chart? Hold on a minute. There it is, yes. Okay, so here's what happens with that one that doesn't. So this is 3n minus 1 over 2n plus 1. We're going to find out. Don't worry, it's going to take about a minute, but we're almost done. 3n minus 1 over 2n plus 1. So I want to know, does this converge or diverge? That's the question. And so what we're going to do is since this does not alternate, we can't use the alternating series test. So notice we kind of jumped ahead and we're like, does it alternate? No, it does not. So I'm going to go way back to the top and we're going to see if this thing converges. So let's go through the list. Bear with me here while I ask you some questions. Number 1, is this geometric? Andrew, is that a geometric series? It's not. Geometric series are when you have something raised to a power, like something raised to the power of n. Geometric, it's right there. There's geometric. Okay, next, is it a p series? All right, Ethan. Ethan, is this a p series? No, it's really not. I mean, you might be able to argue that there's some p series that's related to this, but let's not go there. Okay, not a p series. So next, let's see. So we've done this. We're down here, not a p series. Always check the easy ones first. Now, is the limit equal to 0? Oh, well, let's do that. I mean, that's kind of part of the alternating series test as well, but let's actually do that. What is the limit as n approaches infinity of 3n minus 1 over 2n plus 1? So do that, and then we'll see what you get. I'll give you a sec just to sort of get it straight. You got it? Almost? All right, Eli, do you have this one? Like, what's the limit as n approaches infinity of this? Leading coefficients? Because it's polynomials. Yeah, 3/2. I know. It's like you're used to, it's like we feel like we're shifting gears. It's going to feel like that the rest of the semester. It's hard because we're going back and forth, but we have to do all these. This is 3/2. That is not 0. Well, what does that mean? Oh, wait, if it's not 0, then the thing diverges. Oh, well, then we're done. So this diverges. Okay, so Monday, what we're going to do is we're going to see how we can approximate an alternating series. But for now, I think the homework is all just using the alternating series test. So we're down here. I will add alternating series. Well, maybe I'll do that on Monday, is add the alternating series to my flowchart. I'm going to stop the recording. If you want to chat,